A 2-to-1 position, displacement, and average velocity. A car coasts along a straight road and you glance at the clock. If someone asks, "Where is the car right now?" you might answer, "Near the library," or "At mile marker 12. If they ask, "How much did it move in the last 10 seconds?" you start thinking about how far it progressed. Physics takes those everyday questions and makes them precise, so our description of motion is unambiguous and predictive. Not just a narrative of what already happened. Straight-line motion is an ideal entry point because you can see the modeling clearly without drowning in complexity. In kinematics, we describe motion without explaining its causes. Forces and Newton's laws come later. For now, the goal is a clean, quantitative language built from measurable quantities: position, time, velocity, and then acceleration. You may already want to ask what causes speed to change. Hold on to that question, because separating description, kinematics, from cause, dynamics, is what keeps later reasoning sharp rather than muddled. To make motion problems solvable, we simplify. If the car's size, wheel rotation, or shape doesn't matter for what we're predicting, we treat it as a particle, a single representative point, often the center of mass. The car doesn't become a literal point. The model simply ignores features that don't affect the result we care about. That habit, simplify, calculate, then check whether the simplification was justified, is standard physics practice. Even the question, "Where is it?" depends on conventions. We choose a coordinate system with an origin and a positive direction. Along a straight road, we typically use an x-axis, but the choice is ours. X equals 0 might be your driveway, a signpost, or a sensor. Likewise, east could be plus and west minus, or the reverse. The motion doesn't change, but the numbers do, so being explicit about conventions prevents apparent disagreements that are really just bookkeeping. Because physics is quantitative, units are part of meaning, not decoration. Position is measured in meters, time in seconds, velocity in meters per second. In an expression like v equals delta x over delta t, the units enforce interpretation. ms is a rate of change of position. Careful unit tracking is also one of your best error-checking tools, which is why it's emphasized early in standard texts, Halliday, Ch. 2. Motion itself is change in position over time relative to a reference frame. At rest is never absolute. A passenger can be at rest relative to the bus while moving relative to the road. Physics just requires that you say what frame you're using. In this chapter, the ground is usually the frame because it's convenient and approximately inertial for everyday situations, but it's still a choice. In one-dimensional motion, everything happens along a line, so a single coordinate x suffices. Direction is encoded by sign. If plus x points right, then moving right means x increases, and moving left means x decreases. A minus sign does not mean slower or worse. It means direction relative to the axis you chose. If you reversed your convention, all signed quantities would flip, while the physics remains consistent. Motion diagrams, strobe photos taken at equal time intervals, make these ideas concrete. Imagine a strobe flashing at equal delta t as a ball rolls. Each flash records a position. So the diagram is really position versus time data with the time steps implied. If successive images are equally spaced, the object covers equal distances in equal times. Constant speed. If the direction is also unchanged, then velocity is constant. In one dimension, velocity is speed with a sign. If the spacing grows, the object speeds up. If it shrinks, it slows down. That's still description, not explanation, but it prepares you for the key point. Even in one dimension, velocity, and later acceleration, carries direction. We often represent that direction with a sign rather than an arrow. Plus v means motion in plus x, and negative v means motion in negative x. With a coordinate system set, position is simply the coordinate x. If x equals 0 is a lamppost, and the object is 3 meters to the right, then x equals 3 meters. If it's 2 meters to the left, then x equals negative 2 meters. The origin is arbitrary by design. Physics is usually more interested in changes than absolute labels. Shifting the origin shifts all x values but does not change physical relationships. Displacement is the change in position. Delta x equals x sub f minus x sub I. Here, delta means change in, not delta times. The sign of delta x encodes direction. Delta x is greater than 0 means net change toward plus x, and delta x is less than 0 means net change toward minus x. Displacement is often confused with distance traveled, and separating them early prevents a lot of mistakes. Distance is the total path length along the motion and is always non-negative. Displacement depends only on start and end positions, ignoring what happened in between. Even on a line, back and forth motion makes the difference obvious. If you start at x equals 2 meters, move to x equals 8 meters, and then end at x equals 5 meters, the displacement is. Delta x equals 5 meters minus 2 meters equals 3 meters, but the distance traveled is 6 meters plus 3 meters equals 9 meters. Both are meaningful. They answer different questions. Displacement answers, where did you end relative to where you started? Distance answers, how much ground did you cover? This also clears up a common misconception. Motion does not imply non-zero displacement. You can travel far and still have delta x equals 0 by returning to your starting point. From x equals 0 to x equals 10 meters, and back to x equals 0, the distance is 20 meters, but the displacement is 0. That's not a trick, it's direction built into displacement, so opposite legs can cancel. With displacement defined, average velocity follows immediately. V sub avg equals delta x over delta t, comma, delta t equals t sub f minus t sub I. In one dimension, V sub avg can be positive, negative, or 0 because delta x can be. The sign indicates the direction of the net displacement in your coordinate system. It does not mean how fast in the everyday sense. Average speed is different because it uses distance rather than displacement. Speed sub avg equals distance divided by delta t. Since distance greater than or equal to 0 and delta t is greater than 0 for forward time, average speed is always non-negative and carries no directional information. Two cars can each move at 25 ms, one east and one west, and have the same speed. If east is plus x, their velocities are plus 25 meters per second and negative 25 meters per second. That sign, bookkeeping, becomes essential later when distinguishing head-on motion from motion in the same direction. Motion diagrams connect naturally to averages because they give you positions at equal time steps. If spacing and direction are constant, displacement per step is constant, and the computed average velocity matches that constant velocity. If spacing changes, velocity is not constant. Average velocity becomes a single summary for the whole interval. The crucial point is that V sub avg depends only on x sub f, x sub I, and delta t. You can have a positive V sub avg, even if the object moved in the negative direction for part of the time, as long as x sub f is greater than x sub I. For example, if x sub I equals 0 meters at t sub I equals 0 seconds, and x sub f equals negative 4 meters at t sub f equals 2 seconds, then V sub avg equals negative 4 meters minus 0 over 2 seconds minus 0 equals negative 2 meters per second. The negative sign tells you the net displacement was in minus x. It does not claim the object moved at negative 2 meters per second at every moment. It could have moved rightward first and then leftward farther. Average velocity compresses the whole interval into one ratio, which is powerful but easy to misread if you forget what it averages. That limitation is exactly why we need a sharper idea. Velocity at an instant, not over an interval. Conceptually, instantaneous velocity comes from shrinking the time interval in delta x over delta t down toward a moment, and graphs of x versus t make that relationship geometric through slopes. Halliday Ch. 2. Keeping the pairs distinct, position versus displacement and average velocity versus average speed, gives you precise language for both steady motion and back and forth motion without ambiguity, and it sets up the next step naturally. B. 2 to 2. Instantaneous velocity and speed velocity often starts as an average because averages are what you can compute from two measurements. If a cart is at x equals 2 meters at t equals 1 seconds, and later at x equals 10 meters at t equals 5 seconds, then over that interval its average velocity is delta x over delta t equals 10 minus 2 over 5 minus 1 equals 2 meters per second. But that single number describes the entire 4-second chunk at once. It doesn't tell you whether the cart moved steadily, sped up, slowed down, or even reversed direction in the middle. Physics routinely needs motion right now, because forces, collisions, and control systems act moment by moment, not politely, over long averages. The idea of a velocity at an instant can sound paradoxical at first because any expression like delta x over delta t seems to require a non-zero delta t. The way out is to keep the same ratio, but shrink the interval around the moment of interest and see what value the average velocity approaches as the time window collapses. Calculus formalizes that limiting process. If position is a function x of t, then instantaneous velocity is defined as v of t equals the limit as delta t goes to 0 of delta x over delta t equals the limit as delta t goes to 0 of x of t plus delta t minus x of t over delta t equals dx by dt. The notation dx over dt is not just something to memorize. It encodes a promise about the limit. It says that if you compute average velocities over smaller and smaller intervals, the values settle toward a definite number. When that number exists, it's the velocity right now, in exactly the sense used in standard treatments of one-dimensional motion, Halliday Th2. This definition becomes visually intuitive on a position-time graph. On a graph of x versus t, the average velocity between 2 times t sub 1 and t sub 2 is x of t sub 2 minus x of t sub 1 over t sub 2 minus t sub 1, which is the slope of the straight line connecting the 2 points, open parenthesis t sub 1 comma x of t sub 1 close parenthesis, and open parenthesis t sub 2 comma x of t sub 2 close parenthesis. That connecting line is a secant line, a straight line summary of the motion over the interval. If the position graph itself is a straight line, every second has the same slope, and the velocity is constant. Most interesting motion gives a curved x of t graph. Then different secants give different slopes depending on the interval, reflecting changing average velocity. Now slide t sub 2 closer and closer to t sub 1. The secant line rotates until, in the limit where the 2 points merge, it becomes the tangent line at that time. The slope of that tangent is the instantaneous velocity. So, on an x versus t graph, velocity is read from slope. A steep upward tangent means large positive velocity. A shallow upward tangent means small positive velocity. A horizontal tangent means v equals 0 at that instant. And a downward sloping tangent means negative velocity. Motion in the negative x direction. It's important not to confuse sloping downward with slowing down. On an x versus t graph, downward slope means position is decreasing with time, so velocity is negative. Whether the object is speeding up or slowing down depends on how the magnitude of the slope changes, not whether the curve is above or below the axis. A curve can slope downward more and more steeply. Velocity is negative, and absolute value of v is increasing, so the object is speeding up in the negative direction. Or it can slope downward while flattening toward horizontal. Velocity is negative, but absolute value of v is shrinking, so the object is slowing down while still moving in the negative direction. The graph encodes all of this, but only if you read slope carefully. Once instantaneous velocity is clear, instantaneous speed is almost anticlimactically simple. Velocity is directional, even in one dimension, so it has a sign. Speed ignores direction and keeps only the magnitude. Instantaneous speed equals the absolute value of v of t. If v of t equals plus 3 meters per second, the speed is 3 meters per second. If v of t equals negative 3 meters per second, the speed is still 3 meters per second. The object is just moving in the opposite direction. Everyday language usually reports speed, 60 km/h, without specifying direction along an axis, while physics needs velocity whenever direction matters. A quick hallway image captures the distinction. Choose right as plus x. Walking right at a steady pace gives positive velocity and speed equal to that value. Turn around and walk left with the same pace, and your speed hasn't changed, but your velocity has flipped sign. That sign matters whenever displacement matters, where you'll be after a certain time, whether two objects approach each other, and later, how forces change motion. Replacing velocity with speed in those problems quietly erases direction and leads to wrong but plausible predictions. Motion diagrams and strobe photographs offer the same idea in a more experimental form. If a strobe flashes every 0.10 seconds and a moving object leaves dots at each flash, each dot is a position at an instant. Equal spacing means constant speed. Closer dots mean smaller speed. Wider gaps mean larger speed. Those dots are essentially discrete samples of an x of t graph. Taking an average velocity between two flashes corresponds to a secant slope between two nearby points. Making the flashes more frequent shrinks delta t, and the secant slopes approach the tangent slope, which is the instantaneous velocity. Survey emphasizes this: shrink the interval and watch the average approach the instantaneous logic using numerical tables over decreasing time windows. Survey ch2, and it's exactly the right mental model. Instantaneous velocity isn't a different kind of thing. It's what average velocity becomes when the interval becomes infinitesimal. Because the definition involves a limit, it's natural to wonder whether instantaneous is only mathematical. Real instruments use a small but finite time window, so they report a short interval average. A radar gun samples over fractions of a second. A motion sensor samples many times per second and estimates slope numerically. The calculus definition tells you what value those increasingly short averages are aiming at. If the motion is smooth, the short interval averages cluster tightly around a single number, and that's the instantaneous velocity the theory describes. This is also where a common misconception needs to be dismantled carefully. Average velocity being 0 does not mean instantaneous velocity was 0 throughout the interval. Average velocity depends only on net displacement. If you start at x equals 0 and end at x equals 0, 10 seconds later, then delta x equals 0 and v sub avg equals 0. That statement is equally true if you stood still the whole time or sprinted away and sprinted back. A clean counterexample is an out-and-back walk. Go 10 meters to the right in 5s, then return to the start in the next 5s. Over the full 10s, the displacement is 0, so the average velocity is 0. But the instantaneous velocity was positive during the first half and negative during the second. It may have been 0 only briefly at the turning point. The average velocity tells you where you ended up relative to where you started, not how much motion occurred in between. On a position time graph, that motion rises from x equals 0 to x equals 10 meters, and then falls back to x equals 0. The slope is positive on the way out, negative on the way back, and 0 only at the peak. The secant line connecting the start open parenthesis 0, 0 close parenthesis to the end, open parenthesis 10, 0 close parenthesis is horizontal, so its slope is 0, matching the average velocity. But that secant slope does not match the tangent slope at most points in between. Seeing secant slope is 0 and tangent slope is not 0 side by side is usually enough to make the misconception disappear. Once you're comfortable reading instantaneous velocity as tangent slope, you're already poised for acceleration. Acceleration is about how velocity changes with time, so it will be another slope, this time on a velocity time graph. Kinematics keeps building on one core idea. Average quantities come from secant slopes, instantaneous quantities come from tangents, and the bridge is the limit. Delta t approaches zero. That same logic carries us directly into the next quantity. Sheet I's 2-3. Acceleration velocity describes motion with direction built in. The next natural question is what it means for velocity itself to change. In real motion, changing velocity is the rule rather than the exception. Cars start, stop, and merge. Elevators speed up and slow down. A ball thrown upward steadily loses upward velocity, reaches zero for an instant, then gains downward velocity. The quantity that captures change of velocity is acceleration. As with velocity, the cleanest entry point is an average. If velocity changes from v sub I at time t sub I to v sub f at time t sub f, the average acceleration is a sub avg equals delta v over delta, t equals v sub f minus v sub I over t sub f minus t sub I. The units follow from the definition meters per second squared. It helps to say the unit out loud. An acceleration of 2 meters per second squared means the velocity changes by 2 meters per second every second, on average, over the interval. If a car's velocity goes from 5 meters per second to 15 meters per second in 5 seconds, then a sub AVG equals the fraction 15 minus 5 over 5 equals 2 meters per second squared. The velocity doesn't have to increase smoothly every moment for that statement to be true. It's about the endpoints of the interval. But the same pressure that pushed us from average velocity to instantaneous velocity pushes us here too. Interactions act continuously, so we often want acceleration right now, not just over a long interval. Shrinking the interval around a moment turns the average into an instantaneous quantity, and mathematically that is again a derivative. A of t equals dv by dt. This mirrors the earlier relationship v of t equals dx by dt, Halliday, Ch2. Position changes lead to velocity. Velocity changes lead to acceleration. If the derivative language feels heavy, keep the physical meaning in front. A of t measures how rapidly velocity changes at that moment. In a car, the sensation of being pressed back into your seat is not a sensation of velocity. It's a sensation of acceleration because your body responds to changes in velocity. Graphs make this definition immediately usable. On an x versus t graph, slope is velocity. On a v versus t graph, slope is acceleration. That isn't a separate fact to memorize. It's built into A equals delta v over delta t. The slope of a secant line between 2 points on a v of t graph gives average acceleration over that interval, and the slope of the tangent line gives instantaneous acceleration at a moment. A steep slope means a large magnitude of acceleration. If the slope is steep upward, velocity is changing quickly in the positive direction. If it's steep downward, velocity is changing quickly in the negative direction. A train leaving a station provides a useful picture. If its VT graph starts at v equals 0 and rises gently at first and then more steeply, the acceleration is small at first and larger later. And if the VT graph is a straight line, the slope is constant, meaning acceleration is constant, a special case that will soon let us derive the standard kinematics equations cleanly, Survey Ch2. The most persistent trouble spot is the sign of acceleration, because everyday language tries to replace the physics definition with a shortcut. People use acceleration to mean speeding up, and deceleration to mean slowing down. In physics, that's unreliable because acceleration is directional. In one dimension, it has a sign that depends on your axis choice, and that sign tells you the direction of the change in velocity, not automatically whether speed increases. If we choose plus x to the right, then a positive acceleration means velocity is becoming more positive. That includes going from plus 3 meters per second to plus 7 meters per second, but it also includes going from negative 8 meters per second to negative 2 meters per second. In both cases, delta v is positive. A negative acceleration means velocity is becoming more negative, which includes going from plus 6 meters per second to plus 1 meter per second, and going from negative 1 meters per second to negative 5 meters per second. In both cases, delta v is negative. This is why the shortcut negative acceleration equals slowing down fails. If a skateboarder is rolling left, then v is negative. If they push to gain speed to the left, velocity might change from negative 2 meters per second to negative 6 meters per second in 2 seconds, giving a sub AVG equals negative 6 minus negative 2 over 2 equals negative 2 meters per second squared. Acceleration is negative, yet the skateboarder speeds up because speed absolute value of v increased from 2 to 6 ms. Conversely, a car moving left, negative velocity, can brake and change from negative 10 meters per second to negative 4 meters per second in 3 seconds. A sub AVG equals negative 4 minus negative 10 over 3 equals plus 2 meters per second squared. Acceleration is positive while the car slows down because the velocity becomes less negative, moves towards zero. Survey makes this same point when warning against treating negative acceleration as identical to deceleration. Survey, Chapter 2, discussion of braking. A reliable way to stay oriented is to keep 3 ideas separate. Velocity v carries a sign. Acceleration a carries a sign. Speed is the absolute value of v and has no sign. When you ask speeding up or slowing down, you're asking whether absolute value of v increases or decreases. That question has a simple answer. Speed increases when v and a have the same sign, and speed decreases when they have opposite signs. If v is greater than 0 and a is greater than 0, velocity becomes more positive and the absolute value of v increases. If v is greater than 0 and a is less than 0, velocity is pushed towards smaller positive values and absolute value of v decreases. If v is less than 0 and a is less than 0, velocity becomes more negative and absolute value of v increases while moving left. If v is less than 0 and a is greater than 0, velocity becomes less negative and absolute value of v decreases. Velocity time graphs turn this into geometry. Above the axis, v is greater than 0. Below it, v is less than 0. Upward slope means a is greater than 0. Downward slope means a is less than 0. When the curve moves away from the axis, the absolute value of v increases. When it moves toward the axis, the absolute value of v decreases. Talking about magnitude separately also matters. On a VT graph, the slope itself is acceleration with sign. The steepness reflects absolute value of a. A line sloping down at negative 5 meters per second squared is steeper, hence larger magnitude acceleration than a line sloping up at plus 2 meters per second squared. Whether that makes the object speed up depends on the sign of v at that moment. All of this reinforces a habit that matters throughout physics. Whenever you interpret acceleration, ask yourself what sign convention you're using. Physics doesn't care whether you label right as positive or left as positive. It cares that you stay consistent. If you reverse the axis, every velocity and acceleration flips sign, but the physical motion does not. That's another reason the acceleration equals speeding up shortcut is dangerous. It smuggles in an interpretation that isn't invariant under a change of coordinate sign. With acceleration defined and tied to slopes, the next step is the special case where acceleration is constant. That assumption appears often enough, especially over short time intervals, that it becomes one of the most useful approximations in introductory mechanics. And it's exactly the case where the mathematics simplifies dramatically. D2 to 4. Constant acceleration, a special case. For completely general motion, velocity can change in complicated ways from moment to moment, and you need calculus almost immediately. Introductory kinematics feels powerful because so many real situations are well approximated over a limited interval by constant acceleration. A firm braking event on a level road can be close to constant acceleration for a short time. A car accelerating steadily from a stoplight can be approximated that way for the first few seconds. In freefall near Earth, if we ignore air resistance, the acceleration is essentially constant with magnitude. G is approximately 9.8 meters per second squared downward. The claim is not that acceleration is always constant. It's that it's constant often enough, for long enough, to be a remarkably useful approximation. Halliday H2. Constant acceleration means velocity changes linearly with time. If we choose the starting instant as t equals 0, call the velocity there v sub 0, and call the velocity at a later time t simply v, then v equals v naught plus at. This is not a formula that appears by magic. It's the direct meaning of a constant rate of change. If every second you add the same amount of velocity, then after t seconds you've added at. Position follows from the same logic one step earlier. Velocity is the rate of change of position, so if velocity changes linearly, position changes quadratically. Under constant acceleration, x equals x naught plus v naught t plus 1/2 at squared. The term v naught t is what you would have if you coasted at the initial velocity, and the 1/2 a t squared term is the extra displacement gained, or lost, because velocity is changing during the motion. Many kinematics errors are symbolic rather than conceptual, so it helps to keep each symbol's role straight. X sub 0 is the position at the moment you chose as the start. X is the position later. The symbol t is elapsed time since that start, so it is really delta t, with the start defined as 0. V sub 0 is the velocity at t equals 0. V is the velocity at time t, and a is the constant acceleration during the interval. If you choose a different start, then x sub 0, v sub 0, and t change meaning, but the equations remain correct as long as you stay consistent. Two additional relationships are algebraic rearrangements of the first two, but they are useful because they let you match an equation to the information you have. Eliminating time gives v squared equals v naught squared plus 2a times the quantity x minus x naught, which is ideal when you care about how fast something is moving after a certain displacement and don't care how long it took. Constant acceleration also gives a simple average velocity relationship. Over the interval, v bar equals 1/2 times open parenthesis v naught plus v close parenthesis. So multiplying by time yields x minus x sub 0 equals 1/2 times the quantity v plus v sub 0 times t. This is reliable precisely because acceleration is constant. If acceleration varies, averaging endpoints may fail badly. It's tempting at this point to treat kinematics as a menu of equations. The more durable skill is choosing efficiently and managing signs. The most systematic way to keep control is to choose a coordinate direction at the start and stick with it. If rightward is positive x, then a car moving right has v is greater than 0, even if it's slowing down. Braking corresponds to acceleration pointing left, so a is less than 0. That idea, velocity and acceleration can have opposite signs, is exactly where the everyday term deceleration often causes confusion. Deceleration is not a direction. It's the situation where speed decreases, which happens when v and a have opposite signs. Before using any equation, it helps to write what you know with signs. If a car moves right at 20 meters per second and brakes with constant acceleration, a equals negative 4.0 meters per second squared until it stops, then v naught equals plus 20 meters per second, v equals 0, and a equals negative 4.0 meters per second squared. For stopping time, v equals v naught plus a t is tailor-made. 0 equals 20 plus open parenthesis, negative 4.0 close parenthesis t, therefore t equals 5.0 seconds. For stopping distance, you can use x equals x naught plus v naught t plus 1/2 a t squared now that you have t, but you don't have to. The time-free equation goes straight there. 0 squared equals 20 squared plus 2 times negative 4.0 times open parenthesis x minus x naught close parenthesis implies x minus x naught equals 50 meters. Notice how the algebra forces a positive displacement. That matches the physical story. The car moved to the right while braking, so even though acceleration was negative, displacement remained positive. That small choice, do you want an equation with t or one without, often determines whether a problem feels easy or impossible. If time is unknown and not asked for, using v squared equals v naught squared plus 2 a times quantity x minus x naught can save a step. If a time interval is given, it's usually simplest to use equations that include t. A habit that prevents a lot of pain is solving algebraically before plugging numbers. Rearranging x equals x naught plus v naught t plus 1/2 a t squared to isolate the unknown helps you see the structure and spot mistakes like using "please provide the latex equation you'd like converted to spoken text," where you meant delta x. Many problems quietly set x sub 0 equals 0, and it's easy to forget that was a choice, not a law. If the origin isn't at the starting point, then x and x minus x sub 0 are not interchangeable. The same caution applies to time symbols. Some solutions use t sub f, but what matters is elapsed time. If a clock reads 8:03:12 at the start and 8:03:17 at the end, the physics cares about 5 seconds, not the final reading. If you insist on using t sub I and t sub f, then replace t consistently with delta t equals t sub f minus t sub I. After computing an answer, the sign and magnitude should fit the story. In the braking example, if you mistakenly took a equals plus 4.0 meters per second squared, the stopping time would come out negative. That's rarely a weird physics result. It's the math warning you that your sign choices contradict the physical process. Another look at constant acceleration. The constant acceleration equations hang together so cleanly because they are statements about simple shapes on graphs. Constant acceleration means constant slope on a velocity time graph, so v of t must be a straight line. The value at t equals 0 is v sub 0, and the slope is a. This picture does more than summarize velocity. It gives displacement as area without requiring algebra. Displacement over an interval is the signed area under the vt curve. Under constant acceleration, the curve is a straight line, so the area is a trapezoid. Split it into a rectangle of height v sub 0 and width t, plus a triangle whose height is v minus v naught and base is t. The rectangle contributes v naught t. The triangle contributes 1/2 times open parenthesis v minus v naught close parenthesis times t. Adding them gives x minus x sub 0 equals v sub 0, t plus 1/2 times the quantity v minus v sub 0 times t equals 1/2 times the quantity v plus v sub 0 times t, which is exactly the average velocity relationship. Since v minus v sub 0 equals at, the triangular area becomes 1/2 open parenthesis, at close parenthesis, t equals 1/2 at squared, and you recover x minus x sub 0 equals v sub 0 t plus 1/2 at squared. The factor 1/2 is not mysterious here. It is literally the triangle half inside the area. Motion diagrams tell the same story experimentally. Marks equally spaced in time but growing farther apart show speeding up. Marks shrinking closer show slowing down. Evenly spaced marks mean constant velocity and therefore zero acceleration. Under constant acceleration, the change in spacing from one interval to the next is regular because each time step the velocity changes by the same amount. That pattern is the visual fingerprint of uniform acceleration, Survey-Ch2. Sign conventions become especially clear when you combine representations. If a car moves right, positive. While braking, its velocity is still positive at first, so the VT graph lies above the axis, but the slope is negative because a is less than 0. The line slopes down toward 0. That picture makes it hard to commit a common mistake, thinking negative acceleration means moving left. It doesn't. Negative acceleration means velocity is becoming more negative with time. If the velocity starts positive, becoming more negative simply means decreasing towards 0 and possibly crossing into negative if the motion reverses. The reassuring point is that you do not have to choose between equations, graphs, and words. You use them to check each other. If your algebra says a braking car has delta x is less than 0, even though you defined right as positive and the car never reversed, the area under the VT graph tells you something went wrong, because the graph stayed above the axis, and the signed area must be positive. This habit of triangulating, equations for numbers, graphs for shape, and the story for direction is what makes kinematics feel like control rather than memorization. The next natural application is free fall, where the acceleration is known ahead of time and is approximately constant. The main challenge there is not inventing new equations. It's choosing signs and letting the mathematics describe the motion faithfully. E, 2 to 5, free fall acceleration. Freefall is where the constant acceleration toolkit starts to feel like physics you can watch. Near Earth's surface, the vertical acceleration due to gravity is remarkably steady, so the model fits beautifully, provided we're clear about what we're neglecting. In physics, an object is in free fall when it moves under the influence of gravity alone. That word, alone, matters. A crumpled sheet of paper falls roughly as the equations predict, but a flat sheet experiences air resistance comparable to its weight, and the motion no longer fits the simple constant acceleration form. For now, we neglect air resistance to isolate the clean core idea. Near Earth, a freely falling object has acceleration of essentially constant magnitude. G is approximately 9.80 meters per second squared, directed downward. This is not a speed. It is the rate at which velocity changes. 9.80 meters per second squared downward means that every second, the vertical component of velocity changes by 9.80 meters per second in the downward direction, whether the object is moving down, moving up, or momentarily not moving at all. The most common place students get tangled is the sign, not the value of g. In one-dimensional kinematics, sign is how the equations remember direction. Choose a convention and stick to it. A standard choice is upward, as positive y. With that convention, gravity is always A equals negative g during free fall because gravity points downward. Always refers to the direction of acceleration, not the direction of motion. The acceleration does not flip at the top of the motion. Gravity doesn't care whether the object is rising or falling. Once that convention is set, the constant acceleration equations apply directly with x replaced by y and a replaced by negative g. The velocity equation becomes v equals v naught minus gt, which tells you that an initial upward velocity v naught is greater than 0 is steadily reduced by negative gt, eventually reaching 0 and then becoming negative downward. The position equation becomes y equals y naught plus v naught t minus 1/2 gt squared. And the time-free equation becomes v squared equals v naught squared minus 2g times open parenthesis y minus y naught close parenthesis. These are not separate free-fall formulas. They are the same constant acceleration relationships, with gravity supplying the constant acceleration. The most persistent conceptual trap is the top of a vertical toss. When you throw a ball upward, it slows down, stops briefly, then falls back down. Students often add an extra assumption that when it stops, the acceleration must be 0. That feels plausible if you equate acceleration with speeding up, but acceleration is the rate of change of velocity, and velocity includes direction. At the top, the instantaneous velocity is indeed v equals 0, but the acceleration is still a equals negative g. Gravity is still pulling downward with the same effect as at every other moment, which is exactly why the ball does not hover. Immediately after the peak, the velocity becomes slightly negative and the ball begins moving downward. You can see that directly from v equals v naught minus gt. If v naught is greater than 0, then v decreases linearly with time. Setting v equals 0 gives the time to the peak. 0 equals v naught minus gt, therefore t sub up equals v naught over g. The change from positive velocity to 0 happens only because the acceleration term minus g operates the whole time. If acceleration suddenly became 0 at the top, the velocity would get stuck at 0 and the ball would float, which is not what happens. With upward chosen positive, the trip is also a clean illustration of sign logic. On the way up, v is greater than 0 while a is less than 0, so speed decreases. On the way down, v is less than 0 and a is less than 0, so speed increases. Nothing special happens at the peak except that v changes sign. The acceleration never changes sign. A numerical example makes the equations feel less abstract. Toss a ball upward from y sub 0 equals 1.5 meters, with v naught equals 8.0 meters per second. The time to the peak is t sub up equals v naught over g is approximately 8.0 over 9.8 is approximately 0.82 seconds, at t equals 1.5 seconds. V is approximately 8.0 minus 9.8 times. 1.5 is approximately negative 6.7 meters per second. So the ball is moving downward at 6.7 meters per second. There is no separate going down equation. The sign carries the direction. The maximum height is where the time-free equation shines. At the peak, v equals 0, so 0 equals v naught squared minus 2 g times open parenthesis y sub max minus y naught close parenthesis. Therefore, y sub max minus y naught equals v naught squared over 2g. With v naught equals 8.0 meters per second, delta y sub max is approximately 64 over 19.6, which is approximately 3.27 meters. So from 1.5 meters, the top is around 4.8 meters above the floor. That number is simply the consequence of gravity steadily subtracting from the upward velocity until it reaches 0. Those results also motivate a simple measurement activity. If you could measure the time to the top t sub up, you could estimate v naught is approximately g times t sub up. In practice, the top is hard to detect by eye, so timing the whole flight is easier. In the ideal model, if the ball is caught at the same height it was released, the time up equals the time down, so t sub total equals 2t sub up, and v naught equals g times t sub total over 2. A phone stopwatch might give t sub total is approximately 1.6 seconds, implying v naught is approximately 9.8 times open parenthesis. 0.8 close parenthesis is approximately 7.8 meters per second. The predicted maximum rise would then be delta y sub max is approximately 7.8 squared over 2 times 9.8, which is approximately 3.1 meters. The model's limitations are part of the physics too. Reaction time matters. An error of 0.1 seconds in timing shifts v sub 0 by about 1 meter per second, and since height depends on v naught squared, the height estimate becomes even more sensitive. Air resistance matters more than many students expect, especially for light objects like ping-pong balls. It reduces upward speed more than gravity alone would and breaks the symmetry between up and down times. Even the same height assumption is easy to violate. Releasing at your forehead and catching at your chest changes the timing split and introduces a systematic error if you use t sub up equals t sub total over 2. Graphing the predictions helps reinforce what the signs really mean. Under the ideal model, v of t is a straight line with slope negative g. The top is simply where that line crosses 0. The slope doesn't change there. The position y of t is a downward opening parabola because of the negative 1/2 gt squared term. The top is where the slope of the parabola is 0, but the curvature remains, reflecting non-zero acceleration. This matches the calculus relationship a equals d squared y over d t squared equals negative g, constant throughout the flight. Halliday emphasizes vertical motion precisely because it shows how a simple model can be both mathematically crisp and physically predictive. Halliday, Ch. 2. Once that picture is solid, it becomes a foundation for later topics. In two-dimensional motion, the vertical component will behave exactly like free fall, still with a sub y equals negative g under the same convention, even while the horizontal component does something completely different. Being able to treat vertical motion as its own one-dimensional constant acceleration problem is what makes projectile motion manageable instead of overwhelming. F. 2 Tier 6. Graphical integration in motion analysis. So far, graphs have mostly been about slope. The slope of an x versus t graph gives velocity because v equals dx by dt, and the slope of a v versus t graph gives acceleration because aa equals dv by dt. That slope story is powerful, but it answers only one kind of question. Given the quantity, what is its rate of change? Physics also asks the reverse. Given the rate of change, how much of the original quantity has accumulated? That reverse move is integration, and graphically it appears as area. Start with velocity. If the velocity is constant, displacement is delta x equals v times delta t. On a v versus t graph, constant velocity is a horizontal line, and v delta t is the area of a rectangle with height v and width delta t. That geometry is not a trick, it generalizes. When velocity varies, you can still think in small time slices. Over a tiny interval dt, displacement is approximately v of t dt. Adding those contributions from t sub I to t sub f becomes the integral. Delta x equals x sub f minus x sub I equals the integral from t sub I to t sub f of v of t dt. So, displacement is accumulated velocity over time, and graphically, it is the area under the vt curve. The phrase area under the curve can mislead if you picture area as always positive. In motion, velocity carries a sign, so the integral is a signed area. Where the graph is above the time axis, it contributes positively to delta x. Where it is below, it contributes negatively. For instance, suppose a cart moves right at plus 4 meters per second for 3 seconds, then left at negative 2 meters per second for 5 seconds. On the VT graph, that's two rectangles, one above the axis, one below. The signed area is open parenthesis plus 4 close parenthesis times 3 plus open parenthesis minus 2 close parenthesis times 5 equals 12 minus 10 equals 2 meters. So the displacement is plus 2 meters. It ends 2 to the right of where it started. The total distance traveled is 12 plus 10 equals 22 meters. That difference, displacement versus distance, is exactly the difference between signed area and area without sign, and it echoes the earlier distinction between displacement and distance traveled. The same idea works one level up. Since A equals dv by dt, the change in velocity over an interval is accumulated acceleration. Delta v equals v sub f minus v sub I equals the integral from t sub I to t sub f of A of t dt. On an acceleration time graph, the signed area gives delta v. Again, the sign matters. Positive acceleration shifts velocity in the positive direction. Negative acceleration shifts it in the negative direction. Whether that corresponds to speeding up depends on the sign of v, but the area picture always tells you the direction of the change in velocity. A braking example shows how directly the area interpretation works. If a car starts at v sub, I equals 20 meters per second, and has constant acceleration negative 4 meters per second squared for 3 seconds, the AT graph is a rectangle at negative 4 from ti equals 0 to t equals 3. The signed area is open parenthesis, -4, close parenthesis, open parenthesis, 3 close parenthesis equals -12 meters per second. So V sub F equals 20 minus 12 equals 8 meters per second. No special kinematics formula is required. You are literally adding up how much velocity change the acceleration produces. Graphical integration becomes especially valuable when acceleration or velocity is not constant, and an analytic integral is inconvenient. If a VT graph is a straight line from 0 meters per second at t equals 0 to 10 meters per second at t equals 4 seconds, the displacement is the area of a triangle. Delta x equals 1/2 times 4 times 10 equals 20 meters. That matches the algebraic constant acceleration result because the average velocity is open parenthesis 0 plus 10 close parenthesis divided by 2 equals 5 meters per second, and 5 times 4 equals 20 meters. The agreement is geometry seen two ways. For messy, piecewise graphs, like motion sensor data, you can still estimate displacement by breaking the region into shapes you know. Rectangular-looking sections contribute approximately V delta t. Linearly changing sections are triangles or trapezoids. The trapezoid is particularly useful if velocity changes roughly linearly from v sub 1 to v sub 2 over delta t, then the displacement over that segment is approximately the trapezoid area. Delta x is approximately v1 plus v2 over 2 times delta t. This is not a gimmick. It is what the integral becomes when you approximate a curve by straight segments, which is the core idea behind numerical integration. A realistic example makes the method tangible. Suppose from t equals 0 to t equals 2 seconds, the velocity is roughly constant at 3 meters per second. From t equals 2 to t equals 5 seconds, it rises approximately linearly from 3 to 9 meters per second. From t equals 5 to t equals 6 seconds, it drops linearly back to 6 meters per second. The displacement estimate is the sum of a rectangle and two trapezoids. 3 times 2 equals 6 meters, comma. The quantity 3 plus 9 over 2 times 3 equals 18 meters, comma. The quantity 9 plus 6 over 2 times 1 equals 7.5 meters. So, delta x is approximately 31.5 meters. If a segment dipped below the time axis, its contribution would be subtracted because it represents motion in the negative direction. The same geometry applies to acceleration time graphs. If acceleration is plus 2 meters per second squared for 1 second, then decreases linearly to -2 meters per second squared over the next 2 seconds, then stays at -2 meters per second squared for 1 second, the change in velocity is the sum of areas. The first rectangle contributes plus 2 times 1 equals plus 2 meters per second. The middle segment is a trapezoid with endpoints plus 2 and -2 over 2 seconds, giving signed area 2 plus -2 over 2 times 2 equals 0, so the positive and negative contributions cancel. The last rectangle contributes -2 times 1 equals -2 meters per second. Overall, delta V equals 0. So the object ends with the same velocity it started with even though it experienced acceleration the entire time. That can feel strange until you remember. Acceleration is not motion, it is change in motion, and changes can cancel. The area picture makes that cancellation visible. Graphical integration also provides built-in consistency checks across representations. Wherever x of t increases, v of t should be positive. Wherever x of t has a flat tangent, v of t should be 0. Wherever x of t curves upward like a smile, v of t should be increasing, so a of t should be positive on average there. In reverse, if v of t is a straight line with positive slope, then a of t must be constant and positive, and x of t must be a parabola opening upward. These checks catch errors quickly. If you compute displacement from a VT graph and get a negative delta x, even though the graph is mostly above the axis, you likely subtracted when you should have added computed distance instead of displacement, or misread the axes. If an acceleration time graph is entirely positive over an interval, a negative delta v cannot be correct. Positive signed area cannot produce a negative change in velocity. In longer problems with multiple intervals and sign changes, those sanity checks are often what keeps the solution from unraveling. It also helps to see that the familiar constant acceleration equations are just special cases of these integrals. If a of t equals a is constant, then delta v equals the integral from t sub I to t sub f of AD, t equals a times open parenthesis t sub f minus t sub I close parenthesis, which is the usual v sub f equals v sub I plus a delta t. If v of t equals v sub I plus a times quantity t minus t sub I, then delta x equals the integral from t sub I to t sub f of left bracket v sub I plus a times left parenthesis t minus t sub I right parenthesis right bracket dt equals v sub I delta t plus 1/2 a times left parenthesis delta t right parenthesis squared, which is the standard displacement relation. In this view, the equations don't feel like formulas dropped from the sky. They are areas under simple shapes. A rectangle plus a triangle, because constant acceleration makes v of t a straight line. As you move forward, many motion problems become translation problems. You're given one representation, an acceleration graph, a velocity table, a position curve, and you need another, along with a physically consistent interpretation of direction and magnitude. When you can move comfortably between slope and area, between differentiation and integration, you stop treating graphs as pictures and start treating them as quantitative objects. G. Closing concepts. Straight line motion can feel like a warm-up at first, but its simplicity is exactly why it matters. This is where you learn the grammar of motion. Slopes, areas, and signs. Those ideas keep showing up when motion becomes two-dimensional, and soon after, when forces and energy enter the story. If you can look at a graph and read what it means physically, and if you can keep direction straight by committing to a sign convention, you've built a toolkit that scales up remarkably well. Halliday H2. Much of the early confusion in kinematics comes from blending concepts that everyday language treats as interchangeable. Physics keeps them distinct. Position x is a coordinate label relative to an origin you choose. Displacement delta x is the change in that coordinate. Delta x equals x sub f minus x sub I, and its sign tells you direction along the axis. If you start at x sub I equals 30 meters, and later you're at x sub f equals 10 meters, then delta x equals negative 20 meters. That negative sign is not a commentary on effort. It is the mathematical record that the final coordinate is smaller than the initial one. Velocity is where the graph ideas begin doing real work. Average velocity is v sub avg equals delta x over delta t. The slope of a secant line on an U didn't include the latex expression to convert. Please provide the latex equation you want spoken. For example, x of te equals ae to the j omega t. And I'll convert it to compact TTS-style text like in your examples. Graph. As the interval shrinks, average velocity approaches instantaneous velocity. V equals dx by dt, the slope of the tangent line at a single time. Halliday H2. Instantaneous isn't mystical. It's the value short interval averages aim at as your measurements become more finely resolved. Acceleration fits into the same pattern one level up. Average acceleration is the change in velocity per time, and instantaneous acceleration is a equals dv by dt. The sign of a tells you direction of acceleration along your axis, not automatically whether the object is speeding up. Speed increases when v and a share a sign and decreases when they oppose, because speed is the absolute value of v. A car moving in plus x with v is greater than 0 and a is less than 0 is still moving forward but losing speed. If the same a is less than 0 continues past the moment v equals 0, the car will move in negative x, with v is less than 0. Nothing changed its mind. The sign convention simply tracked direction consistently. Assuming constant acceleration turns the calculus relationships into compact equations. v of t equals v naught plus at, comma, x of t equals x naught plus v naught t plus 1/2 a t squared, comma, v squared equals v naught squared plus 2a times the quantity x minus x naught. These are not magic formulas to memorize. They are the consequences of constant slope ideas applied first to velocity and then to position, exactly as developed in standard texts. Survey Cage 2. Free fall is the cleanest illustration of how much sign conventions matter. Near Earth, gravity provides acceleration of magnitude. G is approximately 9.8 meters per second squared. If you choose up as positive, then A equals negative G. If you choose down as positive, then A equals plus G. The physics doesn't change, only your bookkeeping, and that's the point. A consistent coordinate system turns direction into algebra so you can calculate without guessing. Finally, graphs unify everything by pairing slopes and areas into one visual language. On a v of t graph, area gives displacement. Delta x equals the integral of v of t dt. On an a of t graph, area gives change in velocity. Delta v equals the integral of a of t dt. When graphs reduce to rectangles, triangles, and trapezoids, you can compute these integrals as ordinary geometric areas, and the sign follows from whether the graph lies above or below the axis. All of this sets up the next step, when motion stops living on a single axis. In 2 dimensions, position becomes r vector of t, velocity vector v equals d vector r over dt, and acceleration vector a equals d vector v by dt. Survey Ch 4. The comforting part is that the logic doesn't get replaced, it gets duplicated. You treat the x and y components independently with the same slopes, areas, and sign discipline you practiced here, then recombine them to describe the full motion. If you carry one habit forward, let it be this. Choose your axis, commit to your signs, and let the graphs and derivatives tell you what the motion is doing. That habit is what makes projectile motion feel like an extension of what you already know, rather than a brand new